Yeah, today we will be doing a little bit of geometry, an interesting type of geometry that I hope you guys will enjoy. I think a geometry that you have not seen previously. Yeah, we will. Oh, okay. So let me go ahead and close the public chat. There you go. So now you guys can you guys can chat with me only. Oh no. Okay, hold on. Let me just organize my page here. Sad. Yeah, it was much more fun when. But okay, so that's good for everybody, I hope, because we can this way we can focus on the class rather than trying to answer to each other's questions. Let me first make sure I have a good color here. Awesome. So like I said, so today we will be looking at integer geometry. So the type of objects that we are interested in will be, oh wait, am I recording this session? Yes. The type of objects we will be looking into are triangles, I don't know, squares, rectangles, 3D shapes with integer side lengths, integer area, integer perimeter, all these type of objects. And then maybe next week, I can look into circles and integer radii, in radius, circumradius, and things like that. The reason I like this is because you need to have some good number sense skills in addition to some really primitive geometry, basically. The geometry that I will be mostly involved with would be the like the geometry of right triangles and some really simple objects. All right, so let's start with the first observation, I would say. So suppose that, well, I think everybody know Pythag, right? Pythagorean Theorem. Let's start with this one. You guys love it, right? So what was about Pythagorean Theorem? Yes, the first thing that comes to mind is 3, 4, 5 triangles. Yes, but then now we will go beyond that. So if you have a triangle ABC, we'll try to parameterize all of them with a right angle at, say, C, 90 degrees. Well, the Pythagorean theorem says if and only if what? Well, a square plus b square is equal to c square, because the hypotenuse is at C, so this is the largest of the sides. All right, I will give you a second. If and only if means either direction works. So if you have 3 numbers which satisfy this, then you can build a right triangle. Or if you have a right triangle with sides ABC, then they should satisfy this relationship. So you can go either direction. So if someone gave you 3 numbers which satisfy this relation, then you can certainly build a right triangle around it. So that's the meaning of if and only if. So that's perfectly fine. All right, so either direction, like we said, works. But now the part which is interesting, if you want to parameterize all of these triangles which satisfy this thing, we can start exploring this equation, right? So let's start with this equation and see how far we can stretch this equation. Wow, so you guys are pretty good. So some of you guys already have seen this result, apparently. Well, for one thing, should I write the result first or? Well, okay, so let me write the result first and then let me try to explain where this result comes from. It's very simple idea. So the theorem says the following. If you have ABC are positive integers, ABC are positive integers, and they have no common factors. Oops, let me check my notes, yes. Well, yeah, ABC, the greatest common divisor of ABC is 1. Actually, we will need more than that. We also want the greatest common divisor of A and B, the greatest common divisor of A and C, and B and C to be also 1. The greatest common divisor of B and C. If they are all 1, then we can, oops, I lost my chat box. There you go. Okay, I'm back with my little chat box over here. All right, so then, oh, and then, well, obviously, I also need that, here, remember, the hypotenuse will end up being C, right? I want also A and, yes, so all of these are relatively prime, like I said. So then what? I need a couple of other results. If A and B are opposite parity, well, obviously they cannot be both even, but somehow it's strange that they cannot be both odd, right? So because they are opposite parity, I might as well just choose. So I can choose A odd and B even. Okay, in a minute you will see what I'm about to do. So just bear with me for the time being. Then it is possible to find, so then that's the theorem. The theorem says if you have A, B, C which satisfy these properties, then it is possible to find a U and a V exists. The inverted E means there exists U and V. Okay, or maybe I can just write it. There exist U and V, which are relatively prime, opposite parity, positive, where U is greater than V, such that, okay, let me write all of them. U is greater than V, U and V are opposite parity, opposite, meaning one of them is odd, the other one is even. And what did I say the last one? Oh, and then U and V are co-prime. Their greatest common divisor is 1. Such that, okay, so this is the magical formula now. So I think it will be very surprising if this is the first time you are seeing this result. The legs of your right triangle will end up being U square minus V square. B is equal to 2UV. And C is equal to U square plus V square. I hope you guys have paper, pencil handy right now. Oops. Sorry for that. Oh gosh, okay, there you go. Then, okay, so can you guys type these 3 formulas? So this is important. So this is the first one. So the 2 legs of your right triangle, and this is the hypotenuse. And indeed, if you plug in these numbers into the Pythagorean theorem, it works, by the way. You can just test, replace A with U square minus V square, B with 2UV, and C with U square plus V square. You will see that it definitely works. Now, the proof of this theorem is super easy, but I don't want to spend time here with the proof, or maybe I should, I don't know. Some parts is clear. So the goal is, if we start with this, how in the world do we conclude with this, right? So how in the world do we conclude with such a result, which is, I think it's straightforward. All you need to do is just check it in mod 2. This equation, check it in mod 2. If you check it in mod 2, then you get to the idea that A and B are relatively prime, and then check it in mod 4. Why did I say check it in mod 4? What happens in mod 4 to the A square? What I think we looked at it, yes, previously. In mod 4, a square is either what? What are the residues of a square in mod 4? Yes, that would be either a 0 or a 1. And then similarly, B square, that would be also a 0 or a 1. Yes, so therefore, if both of them were odd, well, the 0 case will happen if one of them is even, right? So if both A and B were odd, then C square would have been equal to 2, but it's impossible. In mod 4, C square is either 0 or 1. So that suggests that A and B, they cannot both be the same parity. So they cannot be both odd, sorry. So establishing both even is easy, because if A and B are both even, then C is also even, which means A, B, C are not relatively prime. You can always, starting with a 3, 4, 5 triangle, you can just multiply by 2 and you can get a new Pythagorean triple. These are easy, so I don't want to do this one, right? So this one is, I want to find different, like Pythagorean triple, like 3, 4, 5 is unique. Another one which you know is 5, 12, 13. I don't want to calculate 10, 24, 20, 26, and so on. Yes. So all I'm interested in is like these ones, or like 5, 12, 13. I'm interested in this one, but I'm not interested in 10, 24, 26, because I can easily get 10, 24, 26 by just doubling all the sides of 5, 12, 13, right? So we have established so far that both A and B cannot be both even, and similarly, A and B cannot be both odd. So A and B have to have opposite parity, like we said here. So I might as well choose A being odd and B being even. right? And then afterwards, it's a very simple, how do you solve an equation like this in number theory? Have you ever done it? This is in Diophantine equations. How do you solve a Diophantine equation like this? Anybody remembers? Um, you almost yes. So in number theory, if you want to solve a Diophantine equation where you have too many variables and too few equations, what you do is you try to factorize the expression. So how can I factorize this expression? A squared plus b squared doesn't factorize. Yes. Okay, quite a few people have, oh, some people are trying the Gaussian primes and stuff. Okay. So what you guys can do is you can move the b squared to the other side, or the a squared. Let's move the a squared to the other side. I know that b is even, right? From now on, we decided b would be even and a is odd, right? So I'm just going to move a squared to the other side. So what we have is b squared is equal to c squared minus a squared. Remember, c is the diagonal. I mean, the hypotenuse, I should say. Hey, how convenient is this? C minus A times C plus A. Remember, B is even, right? So this side is definitely even. It has a bunch of twos in it. Now the question is, what can you say about these two factors? Do they have, what are the common terms of C minus A and C plus A? Yeah, so because, yes. Can you tell me what are the common terms of C minus A and C plus A? Knowing that, okay, so far what we know is A is odd, B is even, and C is odd, right? Why? Because remember that A squared plus B squared is equal to C squared. So far we know A is odd, meaning A squared is odd. B is even, meaning B squared is even. So as a result, C will be also even, right? Okay, so yeah. So as a result, C minus A, an even number minus an odd number. Oh, sorry, what am I saying here? This is odd as well, sorry. All right, so because C is odd, A is odd, so this side is even, this side is even. One thing for sure, C minus A and C plus A, they have a common factor of 2 for sure. Can they have a common factor of 4? C minus A and C plus A? Not really. Why? So think about it. So you have a C. From C, you subtract an A, and then you add an A. What is the difference between C minus A and C plus A? This difference between, yes, that's 2A, but wait a second, we said A is an odd number, so this is equal to 2 times odd. So as a result, because the difference is, if both of them had a factor of 4 in them, their difference would also have a factor of 4. So the fact that their differences only have a factor of 2 suggests that both of them have a 2, at most a 2 in common, right? So now my second question is, so both of them, C minus A and C plus A, they have 2's in them, but they don't have 4's. So meaning, so far our common factor, so our goal is to figure out what is the greatest common divisor of C minus A and C plus A. So far we know it's a 2 for sure. Can it have a 3? Can they have also a common factor of a 3 or a 5, some other stuff in it? Okay, half of the class says yes, the other half says definitely no. Okay. Yeah, the answer is no. Yeah, why is that? Because let's think about it. If C plus A was something, so far we know that C plus A has a 2 in it. And if it had a 3, suppose 3 times, let's say, K, and if C minus A is something like 2 times 3 times L, then their difference, or their sum, let's check their sum, for instance. If you add them up, you get 2C is equal to 2 times 3 times K plus L, right? Oops, K plus L. So, the 2's cancel. Oh, wait. Wait, where did I mess up? Um, This is possible. Okay, I was expecting something. Oh, wait. Do you guys see what happened? So C would end up having what? If that's the case. Okay, I thought that the counter example would come from something else. But do you guys agree that both, wait. This is possible, I think. Wait a second. C would end up divisible by 3, which, wait, where did I mess up? So, which is bad. Why is it bad? A has to be divisible by 3. Oh, yes. That's right. So C would have a multiple of 3 in it as a result, right? But if I subtracted the two equations from each other, in a similar way, I would have gotten 2 times 3 times K minus L. So where the 2's cancel, hey, A also has a multiple of 3 in it. A and C are not relatively prime. I thought they were supposed to be relatively prime, because if A and C are not relatively prime, if they have a common factor, then that same factor will be shared by B as well. So as a result, no, K plus L or K minus L doesn't have to be even. Why? Because maybe one of them is divisible by 4, like let's say wait, maybe not. But this is definitely a violation, right? So that cannot happen. So as a result, we found something fantastic. So there is no other factor. So their greatest common factor of C minus A and C plus A is 2. So then, oh gosh, so that's pretty good. So then we can now exactly say what B squared can be written as. B squared is C minus A times C plus A. Both of them have 2's in them, and then no other factors that they share. So basically, C minus A, you can replace it with something like 2U squared, and C plus A something, or maybe the other way around. So 2V squared, and the other one is something like 2U squared. Do you guys agree? So because the only common factor that you want is a 2. So suddenly when you take the square root of both sides, you would get this, and similarly, their difference and their sum, and boom. So from there, you get the parametrization. Okay, so the proof is, you can find the proof anywhere. So it's, why does it have to be a square? Because, what do you mean, why does it have to be a square? Because, oh, okay, so because obviously the left-hand side is a square, and because these two terms, the C minus A and C plus A doesn't have any common factor, so both of them themselves must be 2 times a square, and then this one should be a 2 times a square. So 2 times a square, 2 times a square. Yeah, so from there, I think, yeah, so the parametrization is there. Now this fun stuff. Okay, this part was maybe not that much fun. The fun stuff is the following. The fun stuff is finding out all the right triangles. All right, are you guys ready? Well, today before the class, I did it on Excel. I won't lie to you. If you have a computer handy right now, you should probably start creating your columns on Excel. So let's do it. So what we will do is the following. So we have a U, a V, oops, let's just extend this, and then A, which is, well, let me do it like this. A is obviously equal to what? U square minus V square, and then we'll have a column of B, which is 2UV, and then a column of C, which is U square plus V square. All right, the rules are the following. Let me remind you of the rules, just in case if you forgot. U should be greater than V. U and V are opposite parity, and U and V, their greatest common divisor is 1. All right, so let's write out all, and they are both positive, obviously. All right, so we are going to, yes, you guys already started listing them. That's pretty good. Okay, you can either do it manually. If you are fast, if you have good numbers and skills, you can do it manually, which is, so yes, opposite parity. So one of them is, so for instance, 2, 1 works. The smallest U you can start with is a 2, and the only number relatively prime to 2 is a 1. So can you plug them into these equations to give me A and B in this case? So plug in 2. So 2 square minus 1 square, that's a 3. 2 times 2 times 1, that's a 4, and 2 squared plus 1 squared, that's a 5. Yes, we did that one. Next one, 3. What is v then? If u is 3, what is v? It has to be 2. Why? First of all, v has to be less than u. And secondly, they have to have opposite parity, and it has to be relatively prime. Plug them in, what do you get? 3 squared 9 minus 2 squared 4. That's a 5. 2 times 3 times 2, that's a 12. And 9 plus 4, that's a 13. Nice. What's the next one? What's the next u and v that I should try? Yes, 4, 1 works because 4 is greater than 1. 4 and 1 are opposite parity. One of them is odd, the other one is even, and they are relatively prime. Make sure they satisfy these 3 properties. So can you plug them in? What do you get? Good, 15, 16 minus 1, 2 times 4 times 1, that's an 8, and then 16 plus 1 is 17. Let's go to the next one, 4, 3, right? Okay, do that one for me. I will lay back and just wait for your answers here. Isn't that fantastic? One of the questions you might ask is, are we gonna miss any right triangle? No. This classification, you can find all of them. That's pretty good, right? So you're not gonna miss any of them. All right, next. What's the next row? What is the next UV that I should try? Is it 5-1 or 5-2, the next one? Can 5-1 work? Yeah, 5-1 shouldn't work, right? Because 5 and 1, they are the same parity. They are both odd. It won't work. So 5-2 is the least one. So you should try 5-2 next. So can you do the calculations? Oops. All right, so. All right, it seems you guys are already up to it. Okay, so 5-2, you get, yes, 21. So which is 25 squared minus, 25 minus 4. And then 2 times, I think this one is a 20, and this one is a 29, 25 plus 4. Next one would be 5-4. Did you guys calculate 5-4? Yes, 9, 40, 41. That's perfect. Let's go to the next row. What's the next one? 5-5 won't do it, right? What should I try next? All right. I'll keep going as far as I can because later on I will use this table. Yeah, so we will go much beyond this, by the way. We will end the class with an open-ended problem, research problem that if you guys are interested, you can keep searching these numbers. Okay, next one is 6-1. I think everybody agreed. The one after that is 6, what's it? Relatively prime. It can't be 3, right? Because 6 and 3 are not relatively prime. Remember, the second condition, this condition says they have to be relatively prime. So the one after that would be 6-5. So can you try 6-1 and 6-5? What do you get? First 6-1. Wow, you guys are good. Yes, so 6 squared is 36 plus 1, and then minus 1. So 35, 12, 37. 35, 12, 37. How about the next one? 6, 5. Yes. Yep. 11, 60, and 61. That's pretty cool. So the next will be 7s. So 7 what? 7-1 won't work because they are the same parity. So they have to be opposite. One of them odd, the other one is even. Yeah, 7-2 works. They are relatively prime. 7-4 works, and 7-6 will work as well. So let's quickly check these. So 7-2, what do you guys get for 7-2? Yes, that's correct. 45, 28, 53. How about 7-4? Oh gosh, this will take us forever today. That's right. 33, 56, 65. These are all different type right triangles. 7, 6. How about 7, 6? Yes. 13, 84, 85. All right, so let's go to the 8s. Let me extend my table. We'll go as far as possible. In the meantime, you guys already can guess what will be the next step, so you guys can continue expanding this thing here. So 8. Oops, come on. There we go. Wait, am I recording this session, right? Oh yeah, we are recording. Don't worry about it. Perfect. Yeah, our recordings are available on our YouTube channel, so you guys can check that YouTube channel as well. Okay, yes, the next one is 8, 1, 8, 3, 8, 5, 8, 7. It's interesting, right? So how many 8s are there? 8, 1, 8, 3, 8, 5, 8, 7. I wonder why there's 4 of them. Yeah, 5, 8. Okay, okay, so 8, 1, if you try 8, 1, it comes out as 63. That's correct. 63, 16, 65. The one after that, 8, 3, comes out as what? 55, thank you. 55, 40, what did you say? 55, 48, 73, thank you. How about the one after that, 8, 5? Is 39, wait, 8, 5 is what? 39, 80, 89, thank you. 39, 80, 89. You can try 8, 7, which is 15. Yes, 15, 112, 113. By now you realize already there's quite a few patterns. I don't know if, well, obviously because I keep going and going. The more you go, you will find out so many interesting patterns. I don't know, you will feel like, wow, I never want to stop and I want to figure out more patterns like the Fibonacci sequence or something like that. It's a pretty cool stuff. Okay, let me finish 2 more things. We have 9, 2, 9, 4, what other? 9, 6 doesn't work. 9, 7 won't work because they are the same odd. Yeah, 9, 8. I think 9, 8. And then 10, 1 and 10, 3. Okay, let me just finish up with this. All right, let me finish with the 10s. Okay, so 10, 5 doesn't work, 10, 7, and then 10, 9. Okay, let's finish all the way up to 10. So this way we can, all right, so 9, 2 would be 77. Like I said, I did it earlier on Excel. This one is 85. The one after that, 65, 72. Oh, wow, you guys also did it. Thank you. 72, 97. How about 9, 8? Yes, thank you. 17, 144, 145, 10, 1. 99, 20, thank you. 99, 20, and 101. And well, 10, 3 is 91. What? 60 and 109. All right, 2 more. 10, 7. 51, 140, yes, 51, 140, and what did you say? 149. Oh yeah, thank you. And last one. Ah, oh, thanks God we saw the end of this torture. Okay, 19, yes. 19, what? 180, 181. Holy. Okay, now, well, let me try to make it tinier. Okay, so this is the smallest I can get. Do you guys see any interesting things here in this picture? I can see quite a few things. Wow. Okay, so you guys are seeing way many more patterns than I did. All right. Yes. Okay, so there's quite a few. Let me actually let me just make it slightly below. Oh, hold on. So yeah, so you guys can see the whole table. Let me maybe highlight the one that I have a couple of questions. One of the questions is the following. It seems like there's always a situation where we have, what is common about these? This line, Say, for instance, this line. What is common among these lines? Yeah, they are one apart. So the hypotenuse is one apart than one of the legs. Is how many of these are there? Is there a finitely many of them, or are there infinitely many cases where this can happen? It seems it keeps happening, but after a while it becomes less frequent, right? So for instance, it happens here again, this one here again. That's an interesting question. So whenever, oh, this happens whenever u minus v is 1. Oh, that's pretty good. So whenever u minus v is a 1, these things will happen. Perfect. Here's another question I have, another pattern, and then I'll move on to the next subject. I'm particularly interested when the two legs of your right triangle, by the way, this is a geometry class and we barely draw any picture. Wait, did we draw any triangle or anything? We didn't even. Okay, so okay, I'll draw a couple of pictures in a few minutes. Okay, I'm particularly interested when the two right legs of your triangle are very close to each other, like let's say 1 unit apart from each other. When does it happen? For instance, it seems it happens here. Does everyone get my question? So I'm checking for the difference of A and B being 1 this time, not B and C or A and C being 1, but A and B being 1. Oh, I skipped a couple of them here. Sorry. Here, oh, no, I didn't. Yeah. Okay, anyhow. Yeah, under what conditions A and B get very close to each other? Here they get very close, 20 and 21. They are just 1 apart from each other. When does this thing happen? Does it happen again? Let me see. It should, I think. Well, not in this picture, but there's, if you keep checking, you will see that, wait, does it happen again here? Let me see. Not in this, yeah, so we need to go larger numbers. Can you tell me what is the next time it will happen again where A and B are 1 apart from each other? A and B, not B and C. A and B being 1 apart from each other. I think it should happen again. Let me see if I have it here in my notes. Yeah, for large, oh yes, I think u equals 12 and v equals 5 can do it. Can you guys tell me what you get if u equals 12 and v equals 5? Yes, that's true. The next time it will happen is exactly when u equals 12. Let's check. And v equals 5. So when you plug them into the expression, what do you get for ABC? Yes. ABC comes out as 119, 120, and what did you say? 169? Okay, thank you. Again, they are 1 unit apart from each other. Now the question is, will they happen forever? So that's a third thing. Like that's a third sequence here. Oops, come on. Yeah, do you guys see that? This kind of, can you tell me when it will happen the next time? So it happened when u was 1, v is 2. Sorry, u is 2, v is 1. Then u is 5, v is 2. Then u is 12, v is 5. What is the pattern? Yeah, so that is very interesting. There's a pattern here, right? Yes, the next one will happen when u is 25, v is 12. Yes. So it seems like all you do is you square the u and you add 1. So okay, so let me see if that's true. I think it is. So for v in the next round, v will take whatever value u was. Okay, let me just do it this way. Hold on, let me go back. Okay, there we go. All right, so this 2 will carry here. And for this value, you just square the 2 and add 1 to it. So 2 squared plus 1. Let's see if it works again. So the next one is 5 carries into the next v. And then, no, it's not squaring, sorry. It doesn't work, right? What is the pattern? I don't know. Or is it times 2? Oh, maybe, yeah, times 2. Sorry. Times 2 plus, wait, no, times 2 plus 1 doesn't work either. I forgot what the pattern is. That was a really cool pattern. Maybe it's times 2 plus, oh, yeah. Okay. I think it is times 2 times 2 plus whatever the v in the previous round is. Yes, yes, yes. Okay, so times 2, 5 times 2 is 10 plus whatever v is in the previous round. Yes, that's 12. Okay, so as a result, the next one would be u times 2 this one. U times 2 is 24. And, oh, sorry, and then we plus v. So 24 plus 5 is 29. And v will be whatever the u in the previous round is. Can you calculate this monster here? A, B, C, check if A, B, and C are 1 apart. A, B, and are 1 apart. So the next one would be u times 2, which is 58. And then add 12 to it, 70. So u equals 70 and v equals 29 will be the next time. Why am I worried about these numbers? When a and b are 1 apart from each other, I can get a particular approximation. What type of an approximation am I told? For instance, think about the 3, 4, 5 triangle. 3 here, 4 here, 5 here. If I take the, yes, if I take the ratio of the hypotenuse to one of the legs, or for instance, the average of the legs. So for instance, 5, okay, so do you guys see that this triangle is kind of similar, not similar, but what do you call it? Approximately the same as here, if this one was a 5, and this one was 5 over root 2, and this one is 5 over root 2, right? So this is a 45, 45, and isosceles triangle. So what we are doing here is we can approximate the number of square root 2, the value of square root 2 by keep using these triangles, right? And each time it will become closer and closer to an ideal 1, 1 root 2 triangle. So that's pretty good as well. Okay, so there are so many patterns here. So for instance, you might want to look at the patterns in the table where all the v's are 1. Do you guys see that's yet another pattern? So let me make it in blue. Check what happens whenever v is a 1 to our triangles. Here, 1 always works, right? Well, not exactly. So whenever u is even, v can be 1. So what type of patterns do you see here? Again, that's something that, yeah, so that might be of interest. Yeah, okay. So like I said, there's so many patterns here. I'll just leave it to you guys to explore. Do you guys want a math counts problem? Okay, here comes a math counts problem. Let's see who will be the first person to solve this problem. All right, so problem. Maybe let me make it a little bit larger. All right, so let's see who is the fastest. So can you find, okay, let me say find all integer right triangles. So ABC integers, positive integers, obviously, right triangles with side lengths ABC, right triangles, where the hypotenuse is 145. The hypotenuse is 145. Can you find all of them? Well, oh, sorry. These are the primitive ones. I just need the ones, like these are called primitive. It cannot be a multiple of any given previous one, right? Actually, it's okay. Okay, it doesn't have to be primitive. Okay, find for me all of them. Okay, wow. You guys already found one. All of them. Okay, give me all of them. And at the end of the class, I'll give you the resource. So far, you guys found one of them. There's 3 more. In total, there should be 4 of them. Yes, second one is found. Liam found the second one. I think I missed the first few. Sorry for that. Yes, Twin Brian found another one. I think Anand found another one. Justin found one. Okay, I think you guys already guessing. Okay, yeah. Okay, so the ones, yes. Yeah, Super Shamik got one. Jenny got one. Yeah, Justin, thank you. All right, so I think everybody found this one. 17, 144, 145. That's one that you guys found. Another one that you guys seem to all found is 105, 100, and the hypotenuse is 145. Another one that I think you guys found is, yes, 143, 24, and 145. And there's one last missing. What is the last one? I'm missing, oh yeah, the 87 guy. Yeah. Okay, 87, 116, and 145. Holy. You guys are fast. All right, pretty good. And try to, like, obviously this is not primitive. Why? Because they are all divisible by 5, right? So which one is primitive here? Oh, people are asking, how did you find the last one? What U and V did you guys use on the last one? Oh, the last one is a 3, 4, 5? Seriously? You guys are smart. Okay, all they did is they multiplied the 3, 4, 5 by 29. Yes. Okay, so basically what you did is you did use a U equals 2, V equals 1, but you used a factor K, factor of 29. So yes. So which of these 4 is primitive? Only this one? Okay, the others are not primitive. You just multiply it out. Oh, 2 of them are primitive. This one is also primitive. All right, can you tell me which U and V you used for this one? U and V? Oh, this is 2021, 20. So this is not primitive either, is it? Oh, 12 and 1. Oh, wow. So U is 12, V is 1. Okay, how about this one? What did you guys use for this one? U and V. 9 and 8. Okay. All right. Okay, looks good. All right, so you guys are in the chat box. You are saying a lot of stuff, like every number has only one primitive. Yes, there's a lot of interesting stuff that you can explore on your own. Yeah, okay, so let's keep further going. So far we investigated the Pythagorean one. So how about a special type of triangle where angle C, so again, you have ABC integers. I want to investigate another very special type of triangle. This triangle will have one of its angles 60 degrees or 120 degrees, not 90 degrees anymore, but this type of triangles. So what would you use? We will no longer use Pythagorean theorem. Which theorem should I use? Not a theorem, a law. Which law do I use here? Law of cosines. Yes. Law of cosines is a generalization of the Pythagorean theorem. And it is extremely useful. And you guys, I'm sure everybody is kind of a professional in this one. Let me remind you of the law. C squared is equal to a squared plus b squared minus 2ab cosine of angle C. But because we are saying that angle C is either 60 or 120, so cosine of 60 is what? 1/2, right? And cosine of 120 is minus 1/2. So therefore, this gives us two different triangles. If C is equal to 60 degrees, that gives us the formula C squared equals a squared plus b squared minus ab. And in the other case, where C is equal to 120 degrees, C squared ends up being a squared plus b squared plus ab. Now our goal is to find all of them. Like we did find all the right triangles, now we will find all, well, when I say all of them, I mean integer side, right? So the side lengths of our triangle will be integer side lengths. All of them. How can I parameterize it? So earlier we did this, right? So the parameterization we found and we proved is this one. If you guys want, I can prove it another theorem to you, but usually it is kind of boring, right? So actually, maybe I should. All right, so let's, it's a very silly idea. I mean, almost straightforward idea. Okay, so let me give you okay, let me not state it as a theorem because maybe theorem is kind of something intimidating. It turns out if you do use this, okay, so let me keep the original. Yeah, here we go. So the original equations are this, right? I want to solve these two equations for all integers, right? So if you use this parameterization, it works. Okay, let me skip the proof. You can find the proof in any, on Google, you just search it, or on AOPS, you can find this proof. V squared minus 2uv. And C is equal to u squared minus uv plus v squared. Holy. Okay, let me have my Excel open in front of me. I want to make sure that we have all of them again. All right, so this is the parameterization. It comes out very easy. I mean, it's based on using one substitution double. And the substitution, do you want to see the substitution? You can do it at home. All you do is in those equations, for instance, start with the first equation. In this equation, all you do is if you plug in A equals U minus W, B equals V minus W, and C equals u plus v minus w, just plug it in, find an expression, and then solve it for w and plug it in one more time. All right, so if you plug in twice, it ends up to this, but it's okay. So I'm not interested in where we got that, but if you do that, you get this final result. All right, here u and v have similar qualifications, but it's a little bit looser than the previous one. The downside of this thing is that, unfortunately, it creates a lot of repeats. All right, so when you put it, it's not like as clear as the Pythagorean triples, so you will get a lot of repeats. That's why maybe using using Excel might be better, because I had to go quite far so that I can find all of them. I'm not missing any of them. All right, so let me see if I have all of them here. Yeah, I have quite a few of them. So the idea, I think the only constraint about u and v is the following. U and v has to be, again, relatively prime. So their greatest common divisor is 1, as usual. And interestingly, u plus v cannot be a multiple of 3. So I don't want u plus v to be divisible by 3, okay? U and v are relatively prime, and 3 does not divide u plus v. Because if it does, then you get, let me see what I get. Yeah, then you got a multiple of an earlier result that you found. You found repeats, which is useless, okay? So are you guys ready? What? Which C is that for? What do you mean? Oh, you don't need this. This is for the proof. If you are wondering where I got this one from, I was just telling the class that you guys can use these substitutions into this equation, and then into one of them, doesn't matter, and then it will boil down to this result, which is pretty cool. So you don't need a W. You don't need a W. All you need is a U and a V. Are you guys ready? Ready? I have so far only Alex said yes. Where's the other yeses? Come on. No. Anant is ready. Thank you, Anant. Yes, dotted calculator. Everybody is ready. Okay, yes, sir. Utai is ready as well. All right, so we will plug in different values of u's and v's. Okay. Oh, one more thing. So this result usually gives you a lot of negatives as well. Whenever there's a single negative, it turns out to be this thing, because it makes sense. If A and B comes out as negative, it means that, I mean, if one of them comes out as negative, I mean, it is clear that we are in the second case. If we have two negatives and one positive, then it means we are in this case. All right. Yeah, this is a little bit more annoying than the Pythagorean triples. Okay, let's begin. All right, so I'm constructing my table again, maybe over here. All right, so we will do quite a few trials and errors. So U, V. Okay, for A, you have the parametrization. We will use A over there. We will use that formula here. We will use this formula next to it, B here. And finally, we will use this one over here. All right, so that should work. All right, so you guys already started. All right, so you guys already started, and suddenly you realize there's a lot of failure, right? So someone tried 2 and 1. It comes out 0, 0, 3, which is a degenerate thing. It doesn't. Okay, so how do I get 1, 1, 1, an equilateral triangle? Yeah, 2, 1 does, yeah, fails. Yeah, it doesn't work. All right, so which value of U and V can I start with? Yes, U and V can both be 1, because there's no longer a, you no longer have to have opposite parity, right? You can start with U equals 1, V equals 1, what do you get? If U equals 1, V equals 1, you get something like -1, -1, 1. I think that's what you get, right? But then what did I tell you earlier? If there are two negatives, it means it's a 60-degree angle. All you do is you just remove the minus signs. That's it. So you found your 1, 1, 1 equilateral triangle. This will never happen again, right? So 2 minuses means 60-degree. Okay, 2 minus sign means a 60-degree triangle. If you end up with 1 minus sign in your calculation, you get a 120-degree triangle. Okay, what's the next one? All right, so we can try quite a few different things. I randomly tried things out. For instance, okay, so let me see. The next one which appears is a 3, 5, 7 triangle. Which values of U and V should I play? Oh, yes. Okay, so you guys already tried it. Okay, try 3, 1. 2, 1 doesn't lead anywhere. Yeah, 2, 1 doesn't lead anywhere. Let me remember. I forgot what 2, 1 leads to. Let me double check. If I plug in 2, 1, Yeah, if you plug into 1, you get 0 minus 3, 3, which doesn't work. Yeah, okay. So 3, 1, try 3, 1. What do you get? I'm wondering, does negative... Yes, 3, 5, 7, right? If you plug in 3 and 1, you get 3 minus 5, 7. But like I said, because there's only a single minus 1, so therefore 3, 5, 7 is a 120-degree triangle. So this is a 120-degree triangle, all right? So I'm just removing the minus sign. It has only a single minus 1. And yeah, so what's that? Why is 3 not u plus v? Why? The reason is because w comes out as divided by 3. If in this system of equations you what's called you isolate the w, it comes out as something over 3. I forgot. Or sorry, it comes out as 3uv over u plus v. So which means if u plus v is divisible by 3, it fails. So that's why we don't want this thing to hold. So this thing shouldn't hold. Yeah. All right. All right. So 3, 5, 7 is a 120-degree triangle. It has also a lot of variations that you can use associated with this. Let's do the following. Okay, for the first time, I'm gonna draw a picture in this geometry class, believe it or not. All right, here comes the geometry picture. I'm a great geometer. Well, Miss Null is a great geometer, so I usually prefer, as you can imagine so far in our classes, I prefer combo. But she's an expert geometer. Okay, so there you go. We have an ABC triangle with 3, 5, 7. We found this. From this triangle, I claim we can find another triangle with a 60-degree angle. We can find 2 of them, 3 of them actually. Which ones are they? Without even trying U and V. I won't even bother trying U and V. I can do a simple trick on this picture and suddenly, yes, good. Yeah, so you guys, not angle bisector, no. Unless there's a trick that I don't know, maybe there's, yes, okay. Drop an altitude, okay. Even better. Yeah, I will drop the altitude in my next theorem. So let me not drop the altitude. Instead, I will extend BC and then do what? Yes, construct an equilateral triangle next to it. 5, 5. Holy, 60, 60, 60. Suddenly, you have this new triangle. Do you guys see that? So this new triangle where this side length is an 8, this one is a 5, 8, 5, 7 triangle with a 60-degree angle. Aha, so that's a better characterization. Okay, so from now on, I'm going to introduce a new notation, which is super cool. Okay, so whenever we have a 60-degree triangle, I will, yes, I will put it like this. For instance, 1, 1, 1 was a 60-degree triangle, and it is not associated, and you cannot do that trick for this one. This is the only triangle which you cannot do it. So whenever we found a 120-degree triangle, like the one we did it here, so let's do it like this, 3, 5, 7, we found that triangle. I can easily find 3 associated triangles with 60-degree angles. And you guys already found one, right? So we can keep the 7, the C we can keep. So this one won't change, that was the C. And in this one, we created 5, 8, 7. Another one that you can create, where can I put another equilateral triangle alternatively? Alternatively, I could have extended this one, and I could have placed an equilateral triangle over here, 3 here, 3 here. Suddenly, our new triangle would be 3, 7, 8. 3, 8, 7, sorry. Yes, 3, 8, 7. Do you guys see that? For every 120-degree triangle that you find, like using the U's and the V's, you can easily construct two 60-degree triangles. Do you guys see that? That turns out to be extremely useful. So that will cut the work that you will do here by half. Yes. Okay, so Twin Brian, he parameterized it. Twin Brian says the following. Whenever you have ABC as a 120-degree triangle, then you can construct A plus B, BC, or A plus B, C as 2 new 60-degree triangles. Whew. Okay, so really good. And by the way, you can easily check, for instance, if I tried u equals 2, 3, sorry, v equals 2, what do you get if I try u3, v2? Yes, that's correct. So you would get one of them. Yeah, if you plug it in, 3 and 2 in our, oh wow, we lost our formula. There you go. All right, so the formula was here, here, and here. So if you plug in 3 and 2, I think this one comes out as -3, -8, and then -3, -8, and 7. Yeah, so because there are two minuses, remember two minuses means, but we didn't have to do it, right? Because we can easily construct the others as well. All right, so interestingly, okay, so can you tell me how I can construct a triangle where C, opposite 120 degrees is 21? C is 21. The side length of C is 21. Can you tell me a 120-degree triangle where C is equal to 21? The length of C here will be 21. Which U and V can I use? Yes. Yes, that's good. You guys are good. Yes. You can have a 15, 9, and 21. If you were to use U equals, oh, wait, I skipped one. Oh, I'm so sorry. Yeah, I just skipped one triangle. Okay, there was another triangle with a smaller C. Sorry. If you try the one that I skipped, which has a smaller C, is 13. I'm trying to order the C's here from the smallest to the larger one. Okay, C equals 13 works. So can you tell me the A and B before we do the C equals 21? For which value of U and V can I find the C equals 13? Yes, that's right. So this one is an 8 and 7, and it works for 4, 1. Yes. If you have a 4, 1, remember U plus V cannot be divisible by 3. Yes. So, and then you can easily find the variations of this. This is a 120 degree. I'm just gonna list the 120 degree triangles, and you can easily come up with the 60 degree triangles on your own, right? So pretty good. So for instance, the 60 degree triangles associated with this one, let me do it one more time. I'm not gonna do it again. 8 plus 7 is 15. So 15, 7, 13. Or you have, what's it? 8, 15, and then 7. So these are 60 degree, well, these are triangles with integer side lengths, which have a 60 degree angle in it. Okay, all right. So the next one is the 21, which you guys told me earlier. So this comes out as a 15 and a 9. What are the U's and V's that support that? The second one doesn't work. Shoot. All right, so double check. Yeah, the minuses might be messed up. Yeah, sorry for that. 8, 15. Oh, sorry. I messed up this one. Sorry. 8, 15, 13, right? Was it like this? Sorry. Yeah, I see. Sorry. Yeah, my bad. Yeah, at home, make sure you do it at using Excel after the class and try to create all of them, right? So it's so much fun. I mean, really good. Like this is an area of math which mixes geometry and numbers. Geometry mixing it with algebra is also fun. So geometry and integer number sided triangles, these type of things have been obviously known to the Greeks. Geometry and algebra, mixing the two, has been just developed pretty much during the 19th century with the work of Galois, right? The abstract algebra. The whole point of abstract algebra, or algebra in itself, why do we do algebra? So that we can understand geometry, right? The purpose of math is geometry, understanding the universe around us. And all the others is kind of supporting that. Like the reason we have algebra, otherwise, what is it about algebra, right? Unless it helps us explain geometry, and it's sometimes hard to see the connection. And the connection is really, it seems, it's abstract algebra. And yeah, that's why I was kind of curious about the Burnside lemma. It's such a natural way to start getting initiated in the whole thing. So you guys can learn it on your own. Okay, counting is also important, obviously. Okay, this one, 15, 9, 21, I tested it. I think it's 5 and 1. So the next one, if you plug in, can you plug in 5 and 2? What do you get if you plug in 5 and 2? I did my 2 minutes. Yes. Okay, 5 and 2, you get 5 minus 16 and 19. That's correct. 5 minus 16 and 19. Because there's a single minus sign. Single minus sign means it's a 120-degree triangle. Perfect. So this one is also a 120-degree triangle, just like this one. All right, so the next one I want you guys to test, or maybe you can tell me. Yes. Oh, 5 plus 1 is, yeah, that's no wonder, right? 5 plus 1 is divisible by 3. Yes. And as a result, we found this weird stuff, which is all sides are multiples of 3. This is what? This is a 5, 3, 7 triangle. Hey, this is just a repeat, right? This one is just a repeat. Yeah, that sucks. We should have avoided this. Sorry for that. Yeah, thank you for reminding me of that. Yeah, we should have avoided this one. Yeah. All right, because it's obvious. So that let me see. Yeah, well, okay. I mean, it's a repeat, but it's well, okay. There will be a lot of repeats. That's no wonder. Okay, how about 6 and 1? What happens if you try 6 and 1? 5, 3, 5, 4, they are all repeats. Wait, did I skip something? 4, 3. Oh, okay. So 4, 3, I skipped. All right. So did I do it on my Excel? Yes, I did it on Excel. I found, yeah, if you try 4, 3, it gives you the 60-degree triangle. 4, 3 will give you 8, 15, 13, which is already here. Yeah, it's already, yeah, part of this guy. Yeah, so you guys need to, I forgot the like, there are some rules because I didn't prove the theorem itself. Right now we are just trying to find the patterns our own, but technically what you guys are supposed to do is prove the theorem. Then with certainty you can say when the repeats happen and how do they happen and things like that. All right, so if you try 6, 1, what do you get? Why is 5, 3 a repeat? If you try 5, 3, I tried it earlier. I got, yeah, 5, 3. If you do it, you will get 21, 5, 19, which is a repeat of 21, 5, 19 is a repeat of 5, 16, 19. Yeah, it's a repeat of this one. Do you guys see that? 5, 3 is a repeat of this one. Why? Because of this theorem that you guys told me earlier. Right. Okay, so if you do 6, 1, you'll get 24, 11, and 31, I think, right? Yeah. Okay, yeah, and then because there's a single minus sign, that means it's a 120-degree triangle. Okay, so let's have the theorem in front of us. Yes, because it's a single minus. I think the minus comes out here, right? All right, so the next one that's of interest, let's go a few more, 3 more. 7, 1, what do you get from 7, 1? If you plug in 7, 1 into the equations. Well, into which equations? Let me have it handy. Yeah, there you go. Into this equation, right? So 7, 1, what do you get? Oh, thanks God. 35, 13, 43, that's correct. 35 minus 13, 43, that's good. So believe it or not, this is the angle opposite C here, which is 43, is 120 degrees in this triangle because it is a single minus sign. All right, so the next one is 7, 2. Can you try 7, 2? And lastly, I will ask you to try 7, 3, basically. That's it. 7, 2, and lastly, 7, 3. I don't want to go further into this. And there's so many patterns again in this type of situations. You guys can double check. Oh, 7, 2 is a repeat. Yeah, it might be. Yes, it is divisible by 3. Yes, if you do 7, 2, it comes out as 21, 24, 39. That's right. Which is, wait, 39, 30, not 29, 39, which is all divisible by 3, yes. So the last case, 7, 3, if you try 7, 3, what do you get? Yes, that's correct. 7, 33, 37, that's it. I don't want to go further all the way to 10, but it's kind of interesting that we were able to, I think the main picture is this one. It's pretty good. The moment you get 120-degree triangles, you would automatically, like you will for free get 2 60-degree triangles as well. All right, so let's take it a little bit further. Well, I have, the good news is if we cannot finish it today, because I have so many 3-dimensional pictures as well, so there's so much fun going on. Okay, yes, buy one, get 2 free, basically. Yes, okay, here's another one. So next we will look at Heron triangles. Have you ever heard of these triangles? Heron triangles. So what is special about these triangles is they have integer side lengths again. Integer, oh, well, okay, so the side lengths are ABC, ABC. They are integer, positive integers. And besides, their area is positive. So the area of the triangle is a positive integer, sorry. And its perimeter is positive, integer again. And the altitude, okay, let me draw another picture here. A, B, C. The altitude here is also an integer. AD is also an integer. AD is an integer. You might ask me, why do you put so many restrictions? Well, because there are so many of them. When I put enough restrictions, there aren't as many. So then suddenly it's an interesting problem. Yes, area is an integer. Perimeter is an integer, and then the height is an integer. You already know one such triangle. Which one is it? Yes, you guys can guess why they call it a Heron triangle, right? Because we need to relate the perimeter to the area, and there's a very convenient formula which does that. Yes. Good. So the way to find area, there's multiple ways. But one of them is extremely convenient. This is an alternative way to find the area of a triangle. Oh, shoot, I don't have enough space here. Okay, there you go. S minus C, there you go. And you can easily relate the perimeter, which is, well, semi-perimeter is S. So it's a pretty good deal. So we will, oh gosh, come on. Okay, okay, good. Well, if you just plug it into the Heron formula, do you want me to cut it short? Let me just cut short the proof. Now, technically, how do we do that? How to prove Heron's formula is, you guys can easily find the proof on YouTube. I'm sure there's dozens of proofs of that. But how can I use the knowledge that I got so far in establishing this result here? How can I A here, B here, C here, and this altitude, let's call it D, for instance. How can I construct based on what I did so far? So far, I learned two things. I learned how to construct right triangles, and I learned how to construct 60-degree or 120-degree triangles. So I know about 60-degree triangles, 90-degree triangles, and 120-degree integer-sided triangles. Ah, good. Evan has a great idea. So far, one person figured what to do. Yes. Okay. So I think there's a couple of people who already got it right. Yes. So the key idea is, yes, let's think about the one that we already know, the 13, 14, 15 triangle. Do you guys remember the 13, 14? Wait, the 14 was this one, right? And then the 15 here. And what was the altitude in this triangle? Yes, the area of this triangle is 84, which is an integer. Obviously, the perimeter is an integer, 42. And finally, the altitude is an integer as well. So it perfectly works for us. So why does this thing work? Because we have, when you investigate this shape, what comes out? Yes. Justin, perfect. Forrest also got it. Yes, because we have two right triangles. We have a 5, 12, 13 right triangle, and then a 9, 12, 15 right triangle. We combine two right triangles, we put them side by side, and boom. Then suddenly we have a triangle like this. This is a situation where we added the two right triangles. Alternatively, we could have subtracted the two right triangles. So meaning we could have put them like this. Let me do it again. So we still have that 9, 12, 15 triangle, and I'm going to subtract that 5, 13 triangle. So suddenly what I'm left with is this triangle right over here. Yes, I got a 4, 13, 15 triangle, and for sure it has an integer area and integer perimeters. All right, so that's the idea. Now let's generalize this idea in this triangle. So the whole point, and you guys already said that, you can also put a 60-degree and 120-degree triangle side by side. Yes. That's not unique in any measure. Yes. So there are some really cool ideas that you guys can utilize in solving these things. Awesome. So let's do it. What is the key idea is then the following. There are two cases. Case one, let me solve case one with you. Case two, you can do it on your own. Okay. Case one is the following. What if D, meaning the length AD, is an even number? Then suddenly, remember our parametrization that we did earlier, right? So the parametrization for ABC was A was U square minus V square, B was, 2UV, right? 2 times U times V, this is a U only. Okay, hold on. U square minus V, this is 2UV, and as a result, C square, C comes out as U, okay, sorry. U square plus V square. Okay, there you go. All right, so all I need is, why don't I create two parameterizations? One of them will be a primitive right triangle. The other one will be a multiple, I will scale it, not a big deal. So as long as I write D as 2UV, because I'm in the even case, right? I will just do the even case now, and then the odd case, you guys can check it later. But for D, I can write it as 2UV, or I can write it as I need to, let's call it P and Q, 2PQ. 9-point circle. Okay, yeah. All right, so then it's easy. All I need is a number, like, so the height, I can write it as 2UV or 2PQ. How can I construct such a number? And then boom, once I have the U and the V, I'm done. So the easiest way to construct such a number would be what? I can start with 4 numbers, U, V, P, Q. And that's it. As long as I pick the U, V, P, Q, the 4 numbers, such that U and V, they satisfy those 3 conditions. P and Q satisfies those 3 conditions that we give it earlier. And then I can easily calculate the other side length, which was, this one is U square minus V square. This one is U square plus V square. This one is P square minus Q square. This one is P square plus Q square. Holy, do you guys see what I'm about to do? I think it's straightforward, right? So does everyone agree what I'm doing? I'm in the case where the altitude is even. And so whenever the altitude is even, I want to construct 2 right triangles next to it. That's why I had to come up with the P and Q as well, right? I need to come up with a UV and then a PQ, and then boom, that's it. You give me 4 numbers, UV, PQ, and then we can easily construct a triangle like this, a Heron triangle. Are you guys ready to do it? All right. So in my case, okay. If you guys want, you guys can at home try on Excel, constructing all the potential cases. But let me give you a couple of them, so you guys we can do it together. So for instance, if I gave you, yes. All right. So remember, our goal is to have 2 times U times V is equal to 2 times, what did we say? P times Q, which means the 2's will cancel in the end. So I want to make sure that I have U times V is equal to P times Q in the most general sense. The best way to do it is the following parametrization. And it's the following. Let me explain. So if I describe U as W times X, V as Y times Z, P as, okay, so you will just see in a minute, just bear with me, W times Y, and then Q as X times Z, then it would do it. So all I need is 4 numbers. And as long as I have these 4 numbers satisfy the following, obviously I want U and V such that what? I want WX to be greater than YZ. And here I want WY to be greater than XZ, right? And obviously the same story, U and V are relatively prime, and well, which will obviously be directly coming out, and P and Q are relatively prime, and then U and V are opposite parity, and so on. So if you do this, then it comes out the following way. Okay, I'm skipping the proof of the theorems. These are all well-known theorems. So for instance, if I give you W, okay, so let's, okay, W is equal to say 2, X is equal to 3, Y is equal to 5, and then Z is equal to 1. Let's see, first of all, if it satisfies these conditions. So W times X, is it greater than Y times Z? Yes. Is W times Y greater than 3 times 1? Yes, again. Okay, so this is, technically, it should work. All All right, so what is the, if based on W, X, Y, Z like this, which triangle am I gonna obtain? What is the U, V, as well as the PQ? So let's start with U, V. What comes out for U and V? Do W, X, Y, Z have to be prime? No, sir. They can be anything. But like I said, so computationally, it's very intensive. So doing it on Excel is, yes, U and V comes out as 6 and 5. How about P and Q? P and Q comes out as 10 and 3. Suddenly you check 30 is equal to 30, works. So it satisfies this condition. So therefore, our altitude will be 60. So let's think about it. So we have, oops. And already you guys can tell me, you can check our, okay, so we found out that 2UV is 60 here. We have a right angle here. And U square minus V square is what? U square minus V square is 11. And U square plus V square is 36 plus, this is a 61. There you go. And then on the other side here, we have P square minus Q square is 100 minus 9, that's a 91. And P square plus Q square is 109. Holy, did I see that? This is one way we can construct it. Another way, so ABC, triangle ABC, and D is here. Alternatively, so the side length here is 102. I think, wait, what's it? Yeah, 102. Alternatively, I could have subtracted, instead of putting side by side like that, okay, let me make it slightly smaller. Let me do it over here. I could have done it the following way. So I could have subtracted it. So this is a 60, that's a 61, that's a 109, and this is a, the whole thing is a 91. This one is 11, so meaning this one is 80. That's it. So we have two different triangles. One of them is an obtuse, the other one an acute triangle. This one is our acute triangle. This one is our obtuse triangle. And both of these triangles have integer area, integer perimeter, and integer side lengths. Isn't that amazing? And you might check the table above. Once you know the altitude, actually life is pretty easy. It's very easy to construct these two things. So the whole idea is try different numbers here. Each time you try a different numbers, you will come up with a different result. This is the case where the altitude is even. If the altitude was odd, then instead of setting the altitude to 2UV, I would have set the altitude to U square minus V square, and the rest is still the same. You would get yet a new parameterization. I'll leave it to you to work it out. But it turns out there's a short formula for all this after you work it out all the way. Yeah, so there's, yeah, but it requires a little bit more math than, I don't want to go over this in this class here. So let me instead give you an example where the altitude is odd. For instance, if you try W equals 3, X equals 5, Y equals 7, and Z equals 1, then U square minus V, well, okay, so first UV. From here, U and V comes out as 11 and 4. And then P and Q comes out as, let me do it. I did it earlier, so you guys can check it later on. So based on this, the triangles that you can create, the altitude becomes, because it's U square minus V square, 121 minus 16, that's 105. So the altitude AD will come out as 105. And you will end up again with two two triangles. One of them is an acute triangle, the other one is an obtuse triangle, and the side lengths are the following. For the acute triangle, AB, or let me just put it, well, okay, AB, BC, CA. I think the acute triangle comes out as 137. Yes, that's the acute one. 137, 233, and BC comes out as, sorry, no, this one's 233, and BC comes out, if you add them, like put them side by side, the right triangles, this one comes out as 88 plus 208. When you do the algebra, that comes out as 296. Or if you subtract them, it will come out as 208 minus 88. So the other triangle would be the same. So 137, BC is 208 minus 88, and finally CA is 233. Okay, so yeah, so that will do. Let me see if my yeah. Okay, so the parameterization is slightly different in this one. I didn't write it, but yeah, so all we did is we wanted to make sure w square minus x square, oh, sorry, u square minus v square is equal to p square minus q square. And then after I moved things around, I found out a parameterization involving w, x, y, and z, just the way we did it here. For u, we did a small trick, so you can basically do a small trick. The parameterization is this, just in case. Let me write out the whole thing, so in case you wonder where we got from here to here. It comes out like, so u comes out as 1/2 wx plus yz. V is 1/2 wx minus yz, and p and q are the same basically. P is, okay, let me write it out, 1/2 wy plus xz, and q is 1/2 wy minus xz. Okay, that's it. So once you have a w, x, y, z, you start with any four numbers, you plug them in, and then you find u, v, p, q, and then you plug it back in again, you find your special triangles. I can see this one being very useful in an HMMT. Wait, I think you meant 208 minus 88. That is correct, which is equal to 120, is it? Yes. So this is an obtuse triangle. This is an obtuse triangle. And this one is an acute triangle. Yeah, this one is an acute triangle. But regardless, both of them has integer areas, which is pretty good. All right. Let me, yeah, there's so many interesting ones. And that, okay, so this one is super interesting. Okay, so I have basically two questions left. Okay, so this one is nice. And I don't think we can finish it all today, but how about you have a rectangular prism? Is that what you call it? A rectangular prism like this. So these are all 90-degree angles, 90-degree angle here, and then 90-degree angle there. All right, so, and the goal is to have positive side lengths, the three side lengths, and then having a positive diagonal, space diagonal. All right, so the space diagonal is this one. Do you know what is the smallest one? Positive side diagonal like this. What is the smallest one which have positive XYZ dimensions, and then 3, 4, 12? No. Wait, 3, 4, 12 works? Oh yeah, it works. 3, 4, 12, 13. Oh wow, but it's way down my list. There's much smaller ones. Can you, what is the smallest one? Which works? Yes. Okay, so far Joseph and Kenneth have the answer. Yes, it's possible to do it with the diagonal 3, the main diagonal. What is it? What are the integer side lengths here? What are the side lengths of this rectangular prism, which will have a space diagonal of a 3? Well, does everyone know the formula? D squared, the length of that space diagonal, is equal to a squared, if a, b, c are the dimensions of the three sides, a squared plus b squared plus c squared, right? Why? Because you start with a squared plus b squared, which is, okay, let's do it here. A squared plus c squared. Let's start with a squared plus c squared. This is a, this is c. So this thing is, because this is a right triangle here, this is a squared plus b, c squared. And then further, if you apply Pythag, oops, let me change the color. This time, if you apply Pythag one more time in this right triangle, why is this a right triangle? Because there's another 90 degree here. A squared plus c squared is one leg. B squared, sorry, this was a b, sorry. Oh my gosh. All right, sorry for that. So this is b squared plus c squared, the square root of it. And this one is an a, sorry for that. This is an a. So therefore, the whole thing, d squared, will end up being a squared plus b squared plus c squared, right? All right, so the first one you can find is the following. You're right. Okay, a, b, c, d. Let me first ask you to construct the triangles, the prisms, and then I'll give you the parameterization in the end. The first one is 1, 2, 2, 3. What is the next one? What is the smallest d? What is the next smallest d that you can get? I claim you can get a 7. Can you give me the dimensions of the 7? The d squared is 49. How can you get a 49? Which squares do you add up to get a 49? There's no smaller between them. You can never get a 4, 5, or 6. So what are the three? Yes, okay, good. A couple of you already guessed it. Dotted calculator has it. S has it. Nate has it. Yes, it is a 2, 3, 4. That's right. Sorry, 2, 3, 6, I should say. So what is the next one? The next one is with a 9. Can you tell me how to get a 9? Actually, there's two ways to get a 9. What are the dimensions of your rectangular prism to get a 9? Not 624, not 632. 148 is one of them. Thank you. What's the other one? So how can you get an 81? Which squares do you get to get an 81? There's another way. Yes. Emma got it. Dotted calculator. Eric got it. Wait, no. Eric, I don't think that works. Wait, does it work? No, you can't have 3669 because it would be a multiple of this one, right? Yeah, you are not allowed to use 3669. Yeah, that's the same as the previous one. The one which works is, yes, it's 744. Yes, if you 7 squared is 49, plus 16 plus 32 is 81. It works. The next one is 11. Can you give me all the primitive 11s? How can you? 11 squared is 121. Why can't I get a shout out? Sorry. Yeah, well, because there are so many people writing on the chat box. Sometimes I'm just missing the yeah, I'm so sorry. Yes. So far, Aiden, Julian, Alex got, yes, 962 works. Give me another one. There's another way to do it. What's the other way to get an 11? Albert, yay. Okay, let's wait for 2 more people. Yes, I need a 121. Which 3 squares, when you add it, can you get a 121? Can D be even? No. No, that's not the one. Wait, 865 works? I don't think it works. Does it work, 865? No, Stephen got it. Yes, Stephen, yes, it works. Yeah, okay, so the answer is 766. Try it. 49 plus 36 plus 36 should give you 121. Yes, good job. Let's do a few more. 13, give me 13. Oh, come on. All right, sorry for that. There is one way to get a 13, 169. Derek, Olivia, perfect. Dotted calculator, good. Let's wait a few more people. No. Leo, give me your answer. Okay, Lerchen, Darren. Okay, yes. It would be, let's wait 2 more people maybe. Justin, can you write your answer again? I didn't see it, sorry. Joseph got it, yes. How can I get a 169 by adding 3 squares? Yes, Justin, that's correct. Yes, it's 3, 4, and 12. Perfect. The next one, and the one after that, the next one is 15, and there's 2 ways to get to 225. What are 2 ways to add 3 squares together? 15. 10, 10, 5 is not, doesn't count because 10, 10, 5 is just multiplying this by 5. 10, 10, 5 doesn't work. Yes. So far, Huey got it. Joseph got it. Dotted calculator got 1. Ethan got 1. Yep. Twin Brian has 1. Isaac has 1. Okay, good. So one of them is 11, 2, and 10. 121 plus 4 plus 100, plus 10, I mean. And the other one is 5, 2, 14. That works. How about 17? 17 works as well. 289. It's getting harder and harder, right? 17. 17 actually works in 2 different ways. And finally, we will do 19 in the end. 19 works in 3 different ways. All right, so far we have Lurchen got 1, Alex got 1, Yuki got 1. Wow, Yuki, you did pretty good. All right, Julian has it. Dotted calculator have 1. Evan, good guess. Isaac, yay. Liam, good. Okay, 112, 12. I think everybody saw that one. 112, 12. What's the other one? Luca, great. 2 to 15 won't work. Because 17 square is 289, not 249, not 229, 289. Yes, the other one is 9, 12, 8. All right, finally, let's do 19. 3 ways to get a 19. And so far, one of them, Isaac got one of them. 2, oh gosh, come on. My pencil is killing me here. Killing me softly. I think that was a song. Okay, 3 different ways to get a 19. Yes. Okay, I think everybody got the 1, 18, and 6. They got 1. And in the end, I'll ask you the pattern. There's a pattern here that I don't know if maybe some of you guys saw it. Yes, Ethan and Yuki got the second one. And I think, yeah, others got the third one. AW, and I missed a couple of people's names. Sorry for that. Yes, Alex also got, Jeremy has one. All right, so the next one I will write is 15, 6, 10. And the one after that is, which one am I missing? Oh, 17, 6, 6, right? 17, 6, 6. Okay, I won't go further. We tried all the ones with a D less than 20. D less than 20, we got all of them. I don't think there's any other with D less than 20. Now, okay, so when you check their parities, what do you guys see? Okay, okay, obviously you can check parity, you can check divisible by 3, all these other stuff. So it would be interesting to check. All right, because we are kind of almost out of time, let me tell you the hint. Either, wait. Actually, yeah, it's more complicated than that. Yeah. It's slightly more complicated. Okay, let me give you the parameterization, and you guys can check at the home different values. Okay, there's a way to find out all of them again. Okay, so that's fun, and it's the following. And any multiple of it works, by the way. P square plus Q square minus U square minus V square. So all you do is guess P, Q, U, V, any numbers that you want, and then plug them in, right? Another one for B and C, it is, B and C are always even, as you can see here. PU minus QV. And by the way, you can please subscribe to our YouTube channel, Momentum Learning YouTube channel, and you can watch these again. So P times V, Q times U plus P times V. And the last one is P square plus Q square plus U square plus V square, right? So that's the whole, and you guys can guess where this is coming from. This is just applying Pythag twice, right? Applying Pythag once, Pythag, because this was the, what was this? Hypotenuse again. Didn't we construct it as hypotenuse in one triangle and then hypotenuse in another one? So it's kind of, the proofs are relatively easy. Well, okay, so this one uses complex numbers a little bit. So maybe if you are very interested, you can search it on the web and you can find some good answers to this one. But yeah, for instance, let me see. Can you guess what the, well, yeah, based on this, it's very easy. For instance, if I tell you that, can you guess a one with a main, with a space diagonal of 25? Yes, the YouTube channel is Momentum Learning, yes. Just search Momentum Learning on YouTube and you can find it. All right. Give me the ABC for a D, which is 25. And I think there's multiple of them. Yeah, and then we are going to, yeah, just wrap it up. I will, as usual, I will wrap it up with an open-ended question. And then that's pretty much it. Okay, let me first figure out what the answer to this one was. Let me see. And then I'll give you a resource that you guys can use if you want to learn more about these type of shapes. Yeah, there's 2 of them. Yes, you guys got one of them. Yes, quite a few of you got it. One of them is 9, 12, 20. 9, 12, 20. Obviously, this comes directly as a multiple of one of them. That one is not interesting. Well, the other one is not interesting either. 15, 12, 16, 25. 15, 12, 16, and 25. Yes, you can find it as a parameterization as usual. But there's so many patterns in this picture as well that you guys can check it later on. The harder problem is the following. Let me give you the harder problem. The harder problem is this. Oh gosh, come on. All right, the harder problem is, can you ever, starting with a three-dimensional rectangular prism again, can you end up with something like this, where the three face diagonals are integers? So integer side length, ABC again integers, but the three face diagonals are integer. Okay, so face diagonal, let me, so for instance, this face here, and then I can try, for instance, this face. These are face diagonal, not space diagonals. So the three side lengths face diagonals. Just as an example, one of them which works is this: 244, 267, and then 125. And it turns out the ABC in those cases are 44, 117, and the B comes out as 240. If you check it, it works. These numbers work. Can you parameterize all of them? That's, yeah, the questions get harder and harder. Here you need to use Pythagorean Theorem parameterization 3 times. All right, let me stop it here. Let me stop the recording here. Thank you guys so much for joining today.